on development of inference for statistical significance. And as you know, Tom is the part of the both FSL and SPM development teams, and that's where he advocates for permutation-based inference testing. So, in his presentation, he wants to do some background review, specifically voxel cluster and true-false significant tests, and multiple testing problem, and then family-wise error or estimate versus permutation, and comparing it to the FDR, false discovery ratio approaches. And then he talks about permutation as a way to measure inference in non-related subjects, and specifically inference for heritability and inference for association. So there are different ways to test for significance that sort of evolved in imaging studies. So on the voxel-wise level, you can test for significance using statistical image values such as t-value or z-value. On a cluster-wise level, there are several measurements of statistical significance that are commonly used in neuroimaging. And those include cluster size in voxels or in units of resolution. There are several combinations that account for both cluster size and image and sort of significance of that cluster, and even more complex combination. And then you can also test for statistical significance of a cluster set where you have several clusters. And finally, you can measure the significance by peak. So it's very common in neuroimaging to derive combined significance based on both cluster size and the intensity information, because clusters can be significant because they have really high significance somewhere along the cluster, or because there are wide swath of voxels that exceed threshold of statistical significance. And both of those are completely valid and physiologically meaningful. You can have activations that are spread out, or you can have activations that are very focused and intense. So there are several historical approaches that account, for example, for cluster mass, and that's approaches by Volmar, or the integral intensity above the threshold, and they're all cluster inference methods. The universal problem is the issue of the cluster forming threshold. So cluster inference is highly sensitive to that threshold value. You set it too low and your activation map or significance map looks ugly. You set it too high and you basically don't have any significance. So where is the happy, unbiased and universal level of significance that gets you reproducible results? For that, there were threshold-free cluster enhancement approaches, abbreviated as TFCE. It's basically a cluster-informed voxel-wise statistic analysis that was published by Steve Smith and Tom Nichols in 2009. And it considers cluster mass voxel-wise for every threshold level, and for a given voxel sums up all the cluster below it. And that basically is the standard approach that I believe FSL is now implements for the significance, cluster level significance. And this is actual statistics that is derived for the TFCE levels. And I really don't know how it all works. All I know is that it works pretty well as an FSL output. And the advantage of using this particular technique is that it avoids the choice of cluster forming threshold, and generally shown to be more sensitive than other cluster-wise inference methods. But yet it is fairly non-specific, because inferences on some clusters basically derive some inference on some clusters for some threshold, and support of effect could be extended far beyond from the significant level. It's now the standard tool by which FSL, does its inference in the randomized technique. Now let's come to the multiple testing problem. This is a fundamental problem for the neuroimaging field because we perform massively univariate modeling, because we fit a model per each voxel and then create a statistical image of the effects. And if we have 100,000 voxels that are entering the model, by pure chance 5,000 of them will be falsely positive voxels with false positive significance. So which of those random number 100 clusters is significant? And here we can actually see that at t level of 0.5 we have large significance. At t level of 6.5 we actually limited to needle point regions of significance. So where is the truth, so to speak? So that problem is not endemic to neuroimaging. It's basically problem of false positive. And there are several ways to address it. One of them is a family-wise error rate, which is existence, basically family-wise error is existence of one or more false positive. And you can define the probability of that false positive error. And another way is false discovery rate, which I'll address later. And there are, of course, other solutions, such as using a full Bonferroni setup and some other maximum distribution methods, such as random field theory and permutations. So Bonferroni basically derives a statistical image based on the number of voxels, and it's the most sort of threshold, it's the most conservative way to correct for it, but it's basically would be completely unrealistic for imaging studies. And there are MTP solutions that are controlling for both error rate with maximum. And again, this is some statistical mumbo jumbo that I really wish Tom was here to explain. And there are, again, maximum distribution methods, and those include permutation, which include parametric methods, which assume distribution of statistics under null hypothesis, or non-parametric methods, which don't actually assume a null hypothesis and instead use data-driven approaches to find distribution of statistics under the null hypothesis. And those non-parametric permutation tests are basically the most universal ways for testing of inference. You can see how this is done. So one of them assumes null hypothesis and Gaussian distribution. The other one doesn't really assume it, but can still identify the significance nonetheless. So here's a toy example for permutation. So we have data from a V1 voxel in visual cortex during visual stimulation. So you have level of significance during active flushing checkerboard experience, and B is non-significance during the sort of passive, just looking at the dark screen. And here we form 6 blocks of measurements, and let's just consider the values we get for the active versus baseline conditions. And you can see that while the figures are variable, the A conditions are typically higher than the B conditions. So our null hypothesis says that there is no experimental effects, and A and B labels are therefore completely arbitrary and therefore completely interchangeable. So A is equivalent to B and B is equivalent to A. So under null hypothesis, we can consider all equivalent relabelings, and using combinatorics, we can basically write them out this way, and then compute all possible statistic values and find 95th percentile of the permutation distribution. And here they are. So we basically have 8 values that are on the 5 percentile, and then we have some values that are not under that, and then we have the 95 percentile. So, and it just so happens that those are the ones where you actually, A and B are not interchangeable. So controlling for the family-wise error rate, we can do it using permutation test, and that's parametric methods that assume distribution of maximum statistic under null hypothesis, and non-parametric methods that again use data-derived approaches. So the strengths of the permutation tests are several. They only require the assumption of interchangeability. So they assume sort of equality of condition under null hypothesis. So under zero hypothesis, HO hypothesis, distribution is unperturbed by permutation, and it allows to build permutation distribution. In this aspect, the subjects can be assumed to be interchangeable. So under each null hypothesis, each subject's A and B labels can be flipped. And fMRI scans actually are not interchangeable under zero hypothesis due to high temporal autocorrelation between them. But the limitations of the permutation testing is computational intensity. So basically analysis require basic analysis are required repeating for several thousand times. But that's sort of alleviated by the very high performance modern hardware that we get. And there is also implementation generality. Each experimental design time needs unique code to generate permutation. But again, that's not so bad for imaging studies. And then there is a requirement for exchangeability, which actually comes out to be quite important in the studies of heritability because subjects are related. The other way to measure false discovery positives or derive measures of false discovery positives are the false discovery rate, or FDR, which is a standard sort of approach where where R voxels are declared active, V is the number of voxels declared positively so, and the observed false discovery rate would be the V over R, and FDR is basically the expectation of this ratio. So here's the how false discovery rate works in the imaging data, where we have noise level, and then we have sound signal level, and then we have signal plus noise. And when we control on the per comparison rate at 10%, or FDR rate of 10%, we can actually recover nearly all of our signal with some of the noise. Now, when we start exercising different, control of family-wise errors at 10%, we can see that, it's actually greatly underestimates, and control of the false discovery rate gives sort of a happy medium at this rate. So the FDR approach is actually quite, good. It's a new approach to the multiple testing. It's easy to apply, and it's adaptive to, fairly adaptive to the study and the signal. And the limitations of it are that number of false positive can be too large for the large sort of signals, and must be sort of accepted and understood by the field because it's a new technique. Now let's talk about permutation of non-independent subjects, and specifically heritability inference and association inference. Now coming back to this approach of modeling the heritability. So we basically have a GLM which we model subject data at one voxel of phenotype, and that's the Y value. And then we have a matrix of covariates, which is the X and B factors. And then we have the covariance model,
which we subdivide into simple additive and environmental components, and then we calculate heritability. And this is basically determined by the kinship structure in phi matrix, and then we perform iterative fitting for this estimate. So again, this is a pedigree and kinship matrix. So pedigree tree is described like that. In the kinship matrix, we record the number of shared genetic material between the subjects in each of the data sets. And on the general linear model, which I call genetic linear model, we have, again, this, and this is our variance, and K is the kinship kernel, and you can see how this matrix sigma, how this variance or matrix sigma is basically dependent on the heritability estimate between kinship and unitary matrix. So the ln likelihood or log likelihood of this expression of the polygenic model is given by this equation, where you basically take a logarithm of the trace of this matrix, but here you actually have to kernel matrix, and that kinship kernel matrix can be as large as 500,000 by 500,000. So it can be a very large matrix. And fitting of this approach is basically, can be very computationally intensive, especially for the second model, where we need to calculate log likelihood between 10 and 20 times to find the maximum log likelihood. And each time a very large matrix has to be inverted. So as you can imagine, that's a big computational problem. So inference on heritability is done, as I mentioned in the first talk, by calculating the null hypothesis, which is sporadic, and that's assumed that heritability is equal to 0. And then we test for the the genetic variance using the likelihood ratio test, where the chi-square gave us the p-value, and those of course would be the uncorrected p-values. And then we need to correct those p-values either by voxel-wise FDR or voxel or cluster-wise family-wise error ratio. And that's where it gets to be not easy. So if we simply want to use FDR for voxel-wise significance, we can do it. But if we want to use the size of the cluster as a measurement of the significance in addition to the sort of intensity of the cluster, this is where the difficulty really arises. We have to come up with a way of performing this inference, and there is no easy way to do it. And there is no easy way to do it because there is a failure of exchangeability. The degree of dependence depends on h squared. And so polygenic matrix is not exchangeable at all because, it's not at all symmetric matrix. While the sporadic matrix is exchangeable, well, but that doesn't help us all that much. So how can we do it? We can compute maximum, likelihood over, all the voxels, and then use this maximum permutation distance to find those threshold parameters for the cluster-based inference. But how can we do this permutation? Well, it's not easy because, again, the subjects are not independent. So we can't just, exchange them between each other. And more importantly, even if we can exchange it, the whole idea of performing this, permutation 10,000 times is ludicrous because it takes forever to do it. So again, it's full MLE modeling is too slow for permutation. So we need approximation solutions that are fast and accurate. And this work is based on a really great paper published by John in 2013, which called the kernel of truth, and that basically posits where the modern genetics should be moving along. So our problem is that we are basically dealing with a multivariate. In this case, it's a bivariate, but in actuality, it's multivariate Gaussian distribution. So there is this two-dimensional dependence of the parameter. Well, fortunately, this dependence can be eliminated by forming an EVD deconvolution or EVD transform that basically makes it from the multivariate Gaussian to two orthogonal univariate distributions which are orthogonal to each other, and basically becomes a problem of not multivariate by multivariable Gaussian distributions. So this in essence becomes, this spread it into the eigenvalues and heritabilities and the so-called, contribution to the sort of complexity of the problem. So eigenvalue decomposition, for those of you who don't know, it's an orthogonal transformation of phenotype data to orthogonal space, where the spaces becomes independent. And what it does, it greatly simplifies the likelihood calculation. So in likelihood calculation, original likelihood calculation, we needed to invert this matrix. In the likelihood after EVD, you see it greatly simplifies into those lambda and tau coefficients that no longer need this inversion. So solar eclipse now fully implements the EVD deconvolution, and to activate EVD you simply use option model type EVD tool. And then you run, you define your trait, then you run a polygenic analysis, and solar eclipse will save the EVD transform data as well as EVD transformation for trait and eigenvalues. And this can greatly accelerate GWAS and family data. However, the likelihood analysis is still iterative, so now it doesn't invert a huge matrix, but it still takes 20 or 30 iterations. Tom has really taken this further by introducing a very clever feature, which we could call informally as hacking the heterosidicity. So following the EVD transformation, the trait values are independent but heterosidastic. So what is heterosidicity? Nobody knows the meaning of that term unless you are a really hardcore statistical boffin. Heterosidicity is when you have a distribution formed from random and independent variable, but with a trend in it. So you have a completely random and independent distribution, but it has a trend in it. So it has a non-zero regression line versus a predictor. In our case, it would be a kinship sort of coefficient that's represented by the taus. So this is an EVD transform trait with heritability in it. You see, it has a trend versus the tau coefficients. And this is EVD trait that's under zero heritability, and it's homozygostic. You can see there is no relationship between them. So Tom has introduced this great approach where we can hack this heterosidicity relationship to perform fast heritability estimates. This of course is just approximation, and you only need to get EVD transform of the kinship. And then you can use single-step regression test to measure heterosidicity, and then sort of relate it, map it back to the heritability. And this can be very, very fast. So this is how it all goes through. Basically, recapitulate what I said before. And now you can basically use simple, linear square regression to calculate the parameters. So that's, zero step is basically just unweighted Newton regression. One step is weighted least square regression. Or, we can go all the way and get a fully converged estimate. Again, here we can do fast heritability test, 3 flavors of the test, either likelihood ratio, which is the optimized one, or either bold ratio, which again is fairly optimized, or just derive a simple score. This is the test that Tom, needs to explain, because I don't quite understand it. But what we basically have is this very fast and very accurate approximation that has some bias, but it actually produces very comparable standard deviation, as well as the mean square error. And we have tried it in the real genetic data, and we basically can get acceleration of up to 1,000,000-fold and get very reliable estimates of heritability. And we can also basically do the same thing for the ACE model for the twins and do it the same way. And we can do accelerated GWAS with related individuals. And, again, AVD association with permutation. Ooh, that's pretty. I don't understand that, so I'm sorry. Ooh. Well, I think, the conclusion is Tom really likes permutations. He's really fond of permutations. He thinks it's the best way to measure inference, and I think he's completely right. What I get out of it is Tom basically, by being so, stubborn about permutation, he basically invented those whole new techniques that will allow Solar to really do voxel-wise calculation of heritability in as little time as several seconds for the whole volume. So what right now takes maybe hours will be resolved in a matter of seconds. And here are the references that Tom has pulled on those developments. And I think that's all for me, and we're basically barely out of time, so if you have any questions,